Okay. The spread of infectious disease is a serious problem and leaves thousands of deaths every year. And influenza is one of these diseases. Using a dynamical model to model the behavior of these diseases would allow us to develop quantitative methods, and with it we can slow or eliminate the spread of these diseases. On the other hand, complex networks field proposes different entities interacting with each other, and this interaction is similar to what happens in an epidemic. And what we're trying to do in this work is to model interaction between different populations in a complex network setting. And we're going to, this is during an epidemic burst, and we're going to use being control, taking advantage of the complex network configuration, and also a neural identifier to identify dynamics of the PNet nodes. We start with the original SIR model, formulated first by Kermack and McKendrick in the 1930s, I believe. And what this does is that it describes the population during an epidemic, and it divides the population in three classes: the susceptible class, the removed class, and the infected class. That's what the letters mean. And we have here that other factors contribute. We have beta, which is the transmission rate, and we have also alpha, which is the recuperation rate from the disease. This model takes into consideration that all of the variables are positive, and that the sum of them, of all of them, is 1, which is the 100% of the population. So, well, as I said, that one was a really old model, and there have been several variations for this model. One of them is the SIR model with seasonality. What this adds is a parameter mu, which is the natality and mortality rate, considered the same in this model. And we have a variable beta, which is a transmission rate. So this is similar, or this adapts to the case when in winter months we have an increase of influenza cases. So we can increase the value of the transmission rate to model this behavior. This model also adds an impulsive control scheme. Well, what it does is that a portion P of the susceptible and the infected class is removed from those classes. That means that a portion of the population is being treated against the disease. Based on this and on the impulsive system theory of Haddad, a former member of our team developed an inverse optimal impulsive control, and this is the equation for the controller. What it does is that it calculates the piece, this portion of people being removed from the susceptible and infected class. I'm going to talk about these values later. Is R2D and P2 are diagonal matrices 2 by 2, and P12 is two-dimensional vector. So on other matters with the dynamic complex network, we have this model for node E, node I, sorry, node I, and we have here the self-dynamics of the node and the interaction with other nodes. This gamma is the inner connection matrix, and we have A, which is from the other connection matrix. We have C, which is the connection strength. And the neural identifier we're using comes from a discrete time recurrent high order neural network, and we can use this model. I'm sorry, is it changing? I forgot.
No, it's not changing.
Uh,
We're watching slide 5.
sorry. Oh, okay. I'm sorry. What this was the inverse optimal impulsive control developed by a former member of our team. And this computes the piece, which are the portion of the class which are being removed, which are being treated against the disease. And this is the dynamical complex network model for node I. And we have here the subdynamics and the interaction with the other nodes. As I said, this is gamma, which is the inner connection matrix. We have alpha, no, not alpha, it's A, sorry. A, which comes from the other connection matrix. We have C, which is the connection strength. So here we have the discrete time recurrent high order neural network model, which is used for the neural identifier. Um, right here we have the adaptive weight vector, and we also have the set of high order connections from nonlinear functions. And well, what we are trying to do here is that we take a complex network and all of the nodes are dynamical systems described by the C model with seasonality. So this will mean that different populations are interacting with one another during an epidemic outbreak. And as I said, we're going to use a pinning control, taking advantage of the complex network configuration. And we're also going to use a neural identifier to identify dynamics of the pinned nodes. So we start with a discretization of the model with the complex network model for node I and the dynamics of the SIR model with seasonality. And this is with a finite difference discretization using a sample time. And it ends up like this. And also the impulsive dynamics only for the pinned nodes. So only the pinned nodes present this behavior. And what is the model? This is the neural identifier configuration.
Daniel, 3 minutes.
Yes. This is the neural identifier configuration. And from this, well, this is P function is a logistic function. And from this, we calculate a real estimated vector. This is a normalization process one below. And normally, we will use the one that is that is above, but we use this normalization process, so all variables are positive and the sum is equal to 1. We train this with the extended gamma filter, and these sequences are well known. In this case, R is equal to 10, and Q and initial P are 2 by 2 diagonal matrices with 10 also as the 32 elements. So from the estimated state, and the estimated state, we adapt the control law developed by Covarrubias as this, and with these parameters below. We make two simulations from this, one with a 5-node network and another one with a 10-node network. These values right here are only for testing. These do not represent anything real. This is the other connection matrix, and we're going to pin control this node. That means we are only treating this node, this population. So these are the results. What we need to see here is that the infected class stays below a level which is roughly below 5% of the population. What we see in the right side plot is the treated people against the disease. We see that we treat all of the infected population and only a portion of the susceptible population. Below we have this population, but in respect to the whole node population. So this means that around 12% more or less is treated, the population of the whole node. We make another simulation with the 10-node matrix, and in this case we are treating only node 1 and 2. Sorry, it was not changing, right?
We are on time, but maybe you can give us the conclusions of your experiments. Since we have no questions, I would like to give you 1-2 minutes to finish your conclusions. So far, we don't have any question. So I'm
Okay.
sorry, the time is over.
Yeah, no, I'm sorry. Well, concluding, we developed this scheme for pinning impulsive neural control for complex networks applied to influenza type A series model. And the results show that by applying the control input only in a few nodes, we can lower the infected levels. And this is not zero, but lowering the infected levels is still something good, and it helps to slow the spread of the disease. And thanks to the neural identifier, we can propose a data-driven approach for unknown models. And we can apply this same scheme used here. Well, I'm sorry for the problems. These were my references.
Thank you, Daniel. Yes,
thank you.
We have to move to the next presentation, but thank you very much for your interesting and timely presentation. And please, we will go to the next. We'll move to the next presentation. I think is Maria Fernanda Lobos. You can confirm if you can.
Yes, I'm here. Hi.
If you can share your screen.
Yes.
Can you confirm that you can do this?
1 minute, please. Okay, sharing.
Yes. Can you make it full screen, or but it works? And can you move? Yes, it works well.
Yeah, is that okay?
Yes, I think so. if there is a button to share the full screen, it will be better, but I think we can see everything.
Yes, you will be able to see everything. I don't know how to.
Okay,
hide
then it works well if you do like this.
Okay.
We can see very well. So, okay, so the next speaker is María Fernanda Lobos from Universidad de Santiago de Chile. And this work is entitled Machine Learning Techniques versus Complexity Theory in Cerebral Hemodynamics of Traumatic Brain Injury patients. So you have 16 minutes and we hope to have some questions.
Okay, thank you, Sebastian. Well, as he said, I'm Fernanda. Hello, everyone. I hope you are enjoying this conference. I will present this work, Machine Learning Techniques versus Complexity Theory in the Cerebral Hemodynamics of Traumatic Brain Injury Patients, that we did along with Robert Alcivar from Universidad Técnica de Manabí, Ecuador, Professor Rooney Panerai from University of Leicester, England, and Professor Max Chacón from Universidad de Santiago de Chile. So, the contents I will go through consider introduction or purpose of the work, the data we used, and considering the methods. I'll talk about complexity theory planes, support vector machines. I'll discuss our results, show our discussion, and finally the conclusion. Okay, so the human brain is one of the most complex organs in existence. Despite considerable advances, however, understanding of its structure and function remains poor. It occupies only 2% of body weight, but it accounts for 20% of body metabolism and 14% of blood flow. Our brain is one of the most tightly regulated of all body organs in our body. Given increases in life expectancy and the increased prevalence of cerebral disease, the importance of cerebral blood flow and its control in physiology and pathophysiology is likely to grow over time. And because of that, there is a growing interest in the understanding of cerebral hemodynamics and associated diseases. As far as we know, hemodynamics is disturbed in traumatic brain injury patients, and also studies have shown that autoregulation is often impaired. Various methods, including mathematical modeling, machine learning models, and transfer function analysis, among others, have been explored to shed light on this topic. Also, there is emerging evidence that analyzing the entropy and complexity of biomedical signals can detect underlying changes in physiology, which are reflective of disease pathology. Okay, complexity entropy planes have shown utility in discriminating healthy subjects from those suffering from pathologies, likely to be a general biological paradigm of classification between pathology and health. An example of this is that complexity of intracranial pressure decreases in traumatic brain injury patients. Okay, so far I have referred to the hemodynamics of our brain, but I have to note that there is a particular mechanism of hemodynamics called autoregulation of cerebral blood flow, a system that manages variations in cerebral blood flow relative to blood pressure. Support vector machine models are able to model this phenomenon, representing the non-linearities of the system. So, what's our purpose in this work? Our purpose is to compare two methods of different paradigms that were able to differentiate between healthy subjects and patients with traumatic brain injury. We compared results obtained from complexity entropy planes versus nonlinear support vector machines models with an autoregressive with exogenous inputs structure. What difference can we find between those two approaches? So to achieve our purpose, we used 5 minutes measurements of spontaneous variations of cerebral blood flow velocity and arterial blood pressure from 30 severe traumatic brain injury patients and 30 healthy subjects. We performed data couplet between the two groups according to age, sex, and side of the brain where the cerebral blood flow velocity was measured. In both groups, the cerebral blood flow velocity was recorded in the middle cerebral artery by means of the transcranial Doppler ultrasound. In TBI patients, arterial blood pressure was continuously recorded with an intravascular catheter inserted into the radial artery. In the case of the healthy subjects, pressure was captured using a non-invasive pressure monitor called Finabres. So about complexity entropy planes we used. Regarding the definition of entropy, we can interpret it as a measure of disorder or uncertainty in a system, meaning that an event that occurs with high probability contains less information than an event that occurs with lower probability. Secondly, complexity is an intrinsic non-trivial behavior of a system. In the current study, complexity was defined as a multiplication of the entropy by the disequilibrium, which is identified with the distance of the system to its state of equiprobable probability distribution. So this probability distribution, PDF, must be computed, which in this case is associated with the time series of cerebral blood flow. The approach introduced by Band and Pomp was utilized in this study to determine the most appropriate PDF due to its simple and robust procedure to capture time causality by considering the relative order of neighboring values in a set of partitions of an observed one-dimensional time series, without prior knowledge of the underlying system that generated it. Let's see an example of this. Imagine here we have a simple signal of cerebral blood flow velocity, where the x-axis represents time or sample, and the y-axis the value of the series at a time or sample. Here above, we have a combination of segments of length 3 that we will later count in our signal sample. By counting the times of appearance of each of the patterns in our signal, and then representing these repetitions in a histogram, I mean, we cut the occurrence from the beginning till the end, the segments of length 3. We represent these occurrences in this histogram. We get then our approximation of our probability distribution function, with which we will compute the entropy. Now, regarding our second method from the machine learning paradigm, we based our model in support vector machines, which are a set of supervised learning algorithms based on the statistical theory of learning that introduced regression as a fit of a tube of radius epsilon to the data. The decision boundary to determine the tube radius is given by a small subset of training examples called support vectors. We then use a radial basis function to implement nonlinear autoregressive models with exogenous inputs. During the training of our models, prediction was made one step ahead and with a dataset independent from the one used in the validation stage. In validation, prediction was made multiple steps ahead. With our model trained, we applied inverse step to the input. simulating an abrupt drop in blood pressure to measure the output response. In simple words, the recovery of cerebral blood flow after an abrupt drop of pressure. So, regarding our results, in the construction of complexity entropy planes, two scenarios were considered. First of all, we consider the analysis of cerebral blood flow velocity signals solely. And secondly, the analysis of changes in entropy and changes in complexity. By changes, I mean cerebral blood flow velocity minus pressure. Note here, and here too, that the orange triangles representing signals from TBI patients tend to be more entropic than those signals from normal subjects, represented by green dots. The same occurs here in scenario number 2. We then build a ROC curve to then compute the area under that curve, which represents the probability of successes of the predictor, in this case, our planes. In the first scenario, a highest 90.18% area under the curve value was obtained with the Salis Euclidean combination, entropy measure combined with the Euclidean distance measure combination. For the second scenario, the best area under the curve was 94.26 that was given by the combination score Salis with the distance measure scooters. So regarding our machine learning models with support vector machines, the training and validation of them were based on different segments of data using a twofold balanced cross validation. Then model performance was measured by the normalized mean squared error and by the Pearson correlation coefficients between the actual cerebral blood flow velocity signal and that predicted by the model. Then we chose the model with maximum correlation coefficients, subject, of course, to the important condition that the model step response was physiologically feasible or acceptable. Well, here we have the average step response of the models selected for each subject for each group, the healthy group and the traumatic brain injury group. We can clearly see that the patient's response is worse than the healthy group. There is a clear deterioration of cerebral autoregulation in the traumatic brain injury patients because the response is lower than the healthy ones. Okay, we have here the drop pressure, and healthy group can recover quite easily to the baseline level, but the traumatic brain injury groups can't have that ability to recover as well as the healthy group. So to know the ability of the methods to distinguish between the healthy subjects and the
2 minutes.
Okay, thank you. We built 3 curves where here we can see that the complexity entropy plane got the highest area under the curve here with 94% of accuracy. The machine learning model obtained an area under the curve of 89.8. Okay, so about the discussion, as I just mentioned, the complexity entropy plane approach shows a stronger capacity to discriminate between both groups than the model's support vector machines. Very important to note that both planes illustrate that biomedical signals from patients with TBI were less complex and less entropic. This probably could point to a simplification of hemodynamics after a head injury. But our models with support vector machine have the capacity to describe the cerebral autoregulation phenomenon dynamically. Our results are in accordance with the proposal that the cerebral blood flow has a more complex behavior than blood pressure, and that there is a loss in the complexity of physiological and behavioral system with aging and disease. The complexity index also of intracranial pressure in other study resulted in a significant predictor of mortality and favorable outcome after a TBI. So, final slide. As a conclusion, our results seem to be consistent with the theory that the decomplexification of a biomedical signal is associated with a pathological condition of the underlying physiological system. The complexity entropy planes yielded better classifiers, but the models have the ability to yield realistic cerebral blood flow velocity responses, step responses to the changes in pressure. This is of interest because for future applications, we can apply clinical and physiological settings. Thank you. Thanks for listening.
Thank you, Fernanda. Nice presentation. We have time for questions. We have one here, Max Chacon. Where are the patients from? I assume where were the data collected?
Yes, the TBI group, traumatic brain injury group, where that data was taken in a hospital in Leicester. I forgot the name. Okay, the healthy group was taken in our university in the Laboratory of Biomedical Engineering and in Universidad of Santiago. And the data from the TBI patients was taken in the university, I'm sorry, in the Adult Intensive Care Unit, Queen's Medical Center in Nottingham, England. Sorry.
Okay, great. I have a comment, more like a question. I don't know if you are familiar with the super functional data. There is a super vector machines model, especially designed for such data where you have like a function. So signal are functions, and there is a special version of super vector machines which has a kernel function that integrates over the whole shape of the functions, called functional super vector machines. It's just, I don't know if you are familiar with that, but it may fit to your problem because it is able to model the function directly instead of doing the two-step approach that you are doing with the time series. Just a comment.
As far as I know, when modeling this phenomenon of cerebral autoregulation, this phenomenon is nonlinear, and the kernel function that is able to model this is the one I mentioned, the radius function.
Yes, it's the same, but designed for functional data, which is non-linear as well, but designed for this kind of data. I can send you the paper.
Okay. I'd appreciate that.
Okay.
Thank you.
We run out of time, so thank you again, Maria Fernanda, and let's move to the next presentation.
Thank you.
I think Fernando Buarque, Joao Amaral, they should be here. Fernando was here, so I can maybe we have to wait a little bit because Fernando was in the conference. In the meantime, I will try to seek the paper I suggest. They are contacting Fernando because he's supposed to be here. Fernanda, this is the paper I mentioned, and we have also a paper on the field, also you combining feature selection for functional data, and we use data of similar characteristics of the one that you have. I mean, it's interesting that the use of kernel functions can model, it gives some flexibility, but you have an extra dimension, which is the time. You have a function data, and how to model this. There are many ways. You can take averages, use wavelets of Fourier functions, but in this paper they do it simultaneously in the kernel, and the kernel is the same. It's an RBF kernel as well, but they consider the integration of the function. So it's a little bit complex, but it's and maybe time consuming. But it's a little bit time consuming, the implementation, but we use it in one paper we published a couple of 1 year ago or something, and it works well. Okay.
Great, I'll check it out. Thank you.
Okay. So we will wait. We hope that Fernando or Joao Amaral appears, and then we have to wait for the next presentation. The next presentation is scheduled at 7:30 at 5:30, so we cannot, and we will wait until 5:30, a little bit earlier, so we can start a little bit earlier with the next one. Mm-hmm. Okay, I think we should resume the session in a couple of minutes. So in the meanwhile, I will ask the authors of the paper 118, I think Karen Medrano is here.
I'm here.
Can you share the presentation to see if there is any problem? And we start in 2 minutes. Perfect.
Okay.
It works nicely. So just in 2 minutes, we will start.
Okay.
Universidad Don Bosco, that is in El Salvador, right?
Yes, it's correct.
Okay. Yes. Great to know that we are represented. We have conference from all over Latin America. So let's see. So I think we should start then. Well, Cesar, you have to resume the recording, or you did it already?
Yes, okay.
Okay, great. Then, well, welcome back to this session, and we have the next presentation will be held by Karen Medrano from Universidad Don Bosco, El Salvador, and the work is entitled "Development of a Computer Platform for the Enrichment of Cultural Environments Using VR and AR." So, okay, you have 16 minutes and time for questions.
Okay, thank you, Sebastian. Good afternoon, everyone. It is a pleasure to be here with you. I attend the Latin American Conference on Computation Intelligence for giving me an opportunity to present development of that computer platform for the enrichment of cultural environments using VR and AR. Three people participate in this project. Bruno Gonzalez, who unfortunately could not join us today, Rene Tejada, who is connected here today, and myself, Karen Medrano. Content. Introduction, we present the current context of cultural centers with regard to your experience. Proposal will be shown the idea of the platform that will help to digitalization of the work in culture centers. Results, we implement the platform, and with the data from it, we build a mobile app for Pinacoteca of the Universidad Don Bosco. In conclusion, we present our observation about the implementation of the platform. This work is framing in the need to develop a digital platform for the creation of virtual reality and augmented reality application, which can be used as support in the culture side for dissemination of this through the use of the interactive interface that enrich the cultural experience of users, being the museum's interpretation centers and archaeological parks place that must incorporate this technology, especially to ensure that new generation of visitors find the digital experience they are looking for, turning this cultural space into place of digital literacy. Currently, the integration VR and ER in museums, interpretation centers, and archaeological parks is enriching the tours and visits to the cultural space. When we talk about enrichment and cultural activities, it is based on the use of technological devices that users carry in their pocket, such as cell phones, cameras, or tablets. It is essential that in order to provide this interactive, it's essential that people may use of their own device in the halls of museums, exhibitions, auditoriums, or archaeological parks. It should be known that this doesn't not present as a problem for this cultural space. Since worldwide, the number of the user with a smartphone exceeds 3 billion and expected to continue to grow gradually over the coming years. The central idea of this work is to implement a web platform based on React language from the website, where the data is texturing in the stored in the Progress PostgreSQL database, except for the image that must be stored in Buforia. For data security, the web application has to the data throw an endpoint with Docker, which will have security for access through user authentication, where the web application must send a JSON web token and the authorization header of the HTTP. A request to the bad API, API, if the authentication is successful, send the web application receive the data in which this can maintain the information displayed in the mobile application. The letter aims to enrich the content of the exhibits and create interactive experience that generate great impact on the user. This is a screen of the auto registration form, in which you enter general data such as name, date of birth, in other associates in which you work at the time of entering the systems. When clicking at the bottom of the front present about, an alert message is displaying information that the data was correctly, and this show in a new row the table locally on right side on the form. In the figure, we can observe how to mobile devices are used for the functionality for the ER application, the functionality of the VR and ER application. Provided VR platform will depend to a large extent on the ecosystem of the mobile device uses, such, for example, GPU or device, the hardware, camera, etc. The terminal platform, the task of the computer descends, presenting the result, while provided server platform, the rest of the processing from the scenario, identification to image composition. The images are processed with maker-based tracking, and markers begin in image or object register, with the application which acts as trigger for information application when the device camera recognizes the market in the real world. While running the mobile application, this triggers the display of virtual connect about the market world position in the camera view. Market-based tracking can also include a quick response code. Where physical markers are reflected, image must be registered in the application in order for them to trigger the displays or the virtual content. So it is important that the image contain distinct shades with complex contour to facilitate the operation of the image recognition and tracking algorithms. Results, the music platform has two components, the web part and mobile part. The web app is developed in React and the mobile part in Unity. In order the AR and VR components inside the application. We also use microservice for storage and authentication of boot components. The test web app component in the mobile application, the web platform was using to digitalize all the information about each paint, sculpture, stained glass, etc. belonging to exhibition of the UDB art gallery. From this information, the mobile application is able to use the device camera to capture the characteristics of a focus object in the real time. In Unity, then use the object feature to generate the ER scenes using neural network, fuzzy logic, and artificial intelligence algorithms. Finally, the create ER scene is displayed on the device screen with the script information corresponding to the focus object. The advantage is the Unity software development kit providing native development support for iOS and Android, allowing the development of portable ER application for both platforms. On your left, can see picture of the stained glass window, Lo Nuestro, the Eva Maria George de Sade. And your right, you can see the RV view provided with the mobile application of this stained glass window. The result too is also the option of virtual tour for the people who cannot physically go to the facility given, then the option of getting to know the catalogs of work. The user experience was measured according to observation and questionnaire conducted to group of the students with the facility of the University of Don Bosco in the case of quantity. Data to multiple choice questions were asked about following aspects. And number one, personal appreciation of the VR application. 3.16% rated the application as defined, while 61.64% rated is acceptable, and 34.62% rated is excellent. Question 2. What is your perception of the 2D and 3D designs of the scenes? 3.65% rated is deficient. 63.85% is acceptable, and 42.31% as excellent. A conclusion: in this World Web Platform was designed and implemented with allow cultural entities to register and digitalize their various work, sculpture, or exhibition sites, regardless of the techniques implemented in it. With this digitalized information, we proceed to communication with a mobile application for the interactive presentation of the works and sculpture to the user. With the experience gaining in the implementation of this platform in a gallery, we are that the web and mobile platform is possible to be applied in other culture, arts museums, archaeological sites, and interpretation center. Thank you for your attention. Question?
Thank you, Karen, for your nice presentation. Do we have any questions from the audience? I have a question. I recall that you used or you have mentioned the use of artificial intelligence, neural networks. In what part?
Yeah.
For recognition, yes.
Yeah, for
So,
recognition image.
Yes, can you tell us a little bit of which architectures you consider? If you use, I don't know, convolutional networks, what kind of artificial neural networks you used for this object recognition step?
In this project, use Buforia. Buforia has algorithms for recognized image. For the algorithm is word only used for recognizing the picture or sculpture used in the project.
Okay. Okay. We don't have any questions, so I think we have a little more time. Any comments from the audience? So, well, then thank you again, Karen, and also Rene, which is also in the audience, to come here all the way from El Salvador to Chile, even if it's online. But thank you for participating, and we will move to the next presentation in a couple of minutes. I would like to see, we have the last presentation will be held, I think, by Renato Tinos.
Hi, Sebastian. I'm here.
Hi, Renato. Good to see you.
Hi.
Can you check if you can upload the presentation?
Sure. Can you see it?
Yes, perfectly.
Nice.
Still, they forced me to wait until, so we start in 4 minutes. Okay.
Okay, no problem.
Mm-hmm. Okay, I think it's time we will continue with the last presentation of the day. Thank you all again for staying at the very end of the conference in this day. And the work we have now is entitled Use of Fitness Sharing in the Local Rule-Based Explanations Method, and it will be presented by Renato Tinos from the University of Sao Paulo. Okay, so you have 16 minutes.
Thanks, Sebastian. Hello, everyone. I hope everyone is fine. My name is Renato. The other authors of this paper, Daniel Santos, he's a master student and the first author of this paper. And the other author is Augusto Baranauskas. He is also a professor here at the University of São Paulo, Ribeirão Preto in Brazil. I will present the paper, Use of Fitness Sharing in the Local Rule-Based Explanations Method. Today, we have the very good machine learning models that present very good performance in many problems. For example, deep learning in image classification. However, the decision made by this algorithm are sometimes difficult for humans to interpret. On the other hand, we have models like decision trees that are interpretable, but they don't present very good performance in many problems. In many areas, we need models that are both have good performance and also be interpretable. And the other problem is that today we have some laws, for example, in the European Union, that controls the use of artificial intelligence and gives the customer the guarantee of explanation. The customer has the right to know why a decision was made by the algorithm. One way to do with this, with explainable artificial intelligence, and one way to work with explainable artificial intelligence is to use surrogate models that are interpretable, and these models are used to explain decisions taken by black box models, for example, artificial neural networks. In this paper, we investigate a model that is agnostic and local. Agnostic means that the model can explain decisions taken by any classifier. And local means that it explains particular decisions taken by the black box model. One model that it's local and agnostic is LIME. It's a very well-known method. And the basic idea is that suppose you have a black box model that generates these decision regions in blue and pink in this figure, and you want to explain the decision taken by this black box model for an instance, for example, this instance in red here. So the basic idea is to generate an artificial data set close to the instance to be explained, and then use this artificial data set to train a surrogate model, and in order to reproduce the decision boundaries close to the instance to be explained. Then we can use this surrogate model to explain the decision taken by the black box model. LOR is another algorithm. The name is local rule-based explanations, proposed in this paper by these authors. And instead of using random distribution to generate the the artificial instance, like in LACCI, they use a genetic algorithm. So the basic idea is to, in this way, to generate artificial instance close to the instance to be explained, and also to cover the decision boundaries close to this instance. Then the LoR gets the artificial data set generated by the genetic algorithm and train a decision tree, and then use this decision tree to explain the instance. It does this by walking the decision trees and explain the instance that needs to be explained. And also what's interesting is that you can also generate the counterfactors that explain why it need to be changed in order to have a different decision. They do this also by walking in the decision tree. So this is the basic idea of LoR. We have an instance to be explained. We have a black box model, for example, artificial neural network that was already trained. Then the genetic algorithm generates an artificial data set with instance close to the instance to be explained, and with decisions, with the same decisions taken by the black box model. And 50% of the instance are generated with the same label, and 50% with a different label. Then it gets this artificial data set and train the decision tree and use the decision tree to get the explanations. Here is the pseudocode of LoR, and we can see that we use two genetic algorithms, one with a fitness function that gets instance closer to the instance to be explained, but and with the same label, and another one with that use another fitness function, and we want to get instance close to this to be explained, but with different label. Then we get these two artificial data sets and train the decision tree. And finally, we extract the rules to explain the decision tree and the counterfactors. What's interesting in LoR is that the authors use and propose to use a number of generations that very small, only 10 generations, and a mutation rate that's high, 0.2. So we ask why the authors are using these particular parameters that are not common in genetic algorithms. So our first hypothesis in this work is that the genetic algorithm employed in LoR does not necessarily preserve the diversity of the population. So the authors are using a small number of generations in order to have a better diversity. But the problem with this idea is that by using a small number of generations, we don't have time to optimize enough the decision boundaries. So we test this hypothesis in some experiments. Here we see the results for the number of generations. Here we use LoR to explain decisions taken by a multi-layer perceptor. In the first row, you can see the original data set for the flame data set. It only has two dimensions in order to check the figures. And we have 4 instances to explain. So in the first row, we see the same data set and the same decision boundaries generated by the multi-layer perceptor. But the instances in red are different, the instance to be explained. In the second row, we have the results of the population generated by the genetic algorithm. And also you can see the decision boundaries generated by the decision tree. And when you increase the number of generations, for example, for this instance, we can see that the diversity becomes lower. We can see this by using the histograms in the border of the figures. And so this explains why the authors are using only 10 generations. Based on these results, we propose the use of fitness sharing in LAR. So our hypothesis is that the use of fitness sharing in the genetic algorithm will improve the diversity, and then we'll have more generations and can have a better optimization of the decision boundaries, and as a consequence, obtain better explanations. So fitness share is a knitting technique using genetic algorithm that penalize solutions that are too close to each other. In LAR with sharing that were proposed in this paper, we modified the fitness function. Here are the original fitness function. We divide by the sum, where n is the number of solutions in the population, and we have this function that penalize when two solutions are too close. We use a parameter, a sigma parameter, that gives the size of the niche. And basically what we do in this paper is to get the genetic algorithm used in LAR and add step 8 that changes the fitness function by using fitness sharing. In the paper, we have two sets of experiments. The first one is testing the impact of the number of generation and mutation rate in LAR with fitness sharing. I already showed some results. And the other experiment, we compare LAR with fitness sharing regarding the classification of instances close to the instance to be explained. We have some results with multi-layer perceptron as a black box model, and also with random forest, but in the paper we show only results for multi-layer perceptron. And we have 3 problems, 2 with only 2 attributes, and 1 breast cancer with 10 attributes. Here are the results for LAR with fitness sharing. We can compare this figure with this one for LAR. You can see here that you have a worse distribution. When you use the LAR with fitness sharing, we obtain better distribution. You can see in the histograms. And also, as a consequence, we can have more generations and obtain better decision boundaries that reproduce the boundaries of the black box model. We have also results in the paper for mutation rates. And here are the results for the second experiment, where we compare the classification of the instance of the original data set that are close to the instance to be explained. For example, when you have 10% of the data set of the instance that are closer to the instance to be explained, here are the results for LAR and LAR with fitness sharing. Here are the results for the F1 score, and we obtain better results for LAR with fitness sharing. S means that the results are statistically significant, and we obtain better results in almost all experiments. In all experiments, but in 2 of them, they are not statistically significant. When you use 10%, 20%, or 30%. Here are an explanation of an example of an explanation for the breast cancer data set. Here is the explanation for LAR. So in LAR, in this example, it uses only 1 attribute the mean perimeter of the size of the tumor to explain the decision. And in LAR with fitness sharing, you have a more complex decision that use more attributes to explain the decision taken by the black box model. In this case, the artificial neural network, the multilayer perception. And here are the counterfactuals, what we need to do to change the decision. For example, if you change this attribute to these values, we will have a different decision. So in conclusion, we analyzed the impact of the genetic algorithm parameters in LAR and verified that the diversity is, the final populations have low diversity, so the decision boundaries are not so good. So we propose the use of fitness shares in order to have a better diversity, and then we can have more generations and obtain better decision boundaries. As a future works, we want to use the LAR with fitness sharing to explain decisions in medical problems. For example, the classification of EEG signals, investigate overfitting regarding the size of the decision tree, and also investigate how to detect and preserve borderline instances close to the decision boundaries. And finally, use efficient recombination mutation operators in the genetic algorithm. So this is it. Thank you very much. Thank you.
Thank you, Renato, for your very interesting talk. We have time for questions. I have a question. I noticed that you use like really small data sets, small benchmark data sets such as Wisconsin breast cancer. I don't know if the original method is bottlenecked in terms of complexity and it makes it slow, or the choice of the data set is because of the visualization. I noticed your visualizations, of course, doesn't really work with big data sets, but I really would like to know a little bit more about the complexity of the original model, LAR, and your version, which seems to be a little bit more efficient, and if these strategies can handle larger data set than breast cancer or flame.
Right. The first two data sets we choose because they have only two attributes in order to visualize the graphs. The third data set, breast cancer, 10 attributes, but almost 700 instances. In fact, there is a problem because every time that you need to explain an instance, you need to run two genetic algorithms. So we have genetic algorithms not so fast. You have maybe some minutes to have a result. It can be used in instances more, in data sets with more instances, but the problem in this case is that you have more time to obtain the results. But no problem. We can use for larger data sets. The only problem is that you need to wait a little bit more to obtain the results.
Okay, thank you, Renato. I have a second question. Rocio Ochoa asked, how does population size influence model performance?
Right, both are good questions. In fact, I didn't show the parameters. The number of individuals in the population is 1,000. We didn't show here everyone, because if two instances are too close, we didn't show. In fact, if you have a larger population size, we have more time. We need more time to run the results. So we need to wait more to have a decision. I think the method is good to explain. It's not good to explain something that you need seconds to, if you need to explain a decision in seconds. But if you have minutes, it's okay, no problem, even with a large population size.
Okay. I think we are on time. Before I close this session, I invite you all to the results of the thesis contest that will be announced in this room. So now I thank you all the speakers for these very interesting talks. I can make one applause in representing everybody, and well, then we soon will start the thesis context results. So thank you all. Thank you.
And thanks, Sebastian, for sharing this session and everyone in the backstage. Thanks.
Bye.